Let's have a recap from our previous video. Hello guys, you are welcome to this lecture. If you've not subscribed to this channel, please make sure that you subscribe to this channel, turn on the notification button so that you'll be notified whenever we post a new video. Now, in our last lecture, we talked about the E and Z configuration for naming isomers. Now we said that the E and Z configuration is for nomenclature of unsaturated systems which cannot ordinarily be named by the cis and the trans. Now in the E and Z configuration, what I said was we have to share this thing into two with our eyes. If you are opportune to do this with your pencil, you can do it, or if you can just gaze at it and then know what you want to do, then it's fine. Now what you are going to do is assign priority to the atoms that are bonded to the carbon at the seat of the double bond. Now this is the seat of the double bond. This carbon here and this carbon here are the seats of the double bond, and then we have to assign priority to the atoms that are present at this seat of this double bond in such a way that priority is assigned in accordance with atomic number. The atom that have the highest atomic number automatically have the highest priority. So in this case now, we are going to break CH3 to C, H, 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 and then we'll have Cl. Now between chlorine and carbon, we shall have the highest priority. Chlorine have the highest priority, and I said the one with highest priority, let's say we name it as A. The one with lowest priority, let's give it what? B. Now how about B arrow? B arrow and hydrogen, we shall have the highest atomic number. Of course B arrow have the highest atomic number, so this is A and then this is B. Now whenever the two highest priority group are on the same side, for instance A is here, they're on the same side, what do you call it? You call it the Z configuration or susamem, which means together. Z configuration. How about this? Whenever you have this is now in this case, of course we know that these have the highest priority here, why this have the lowest. Now here bromine have the highest, why this have the lowest. Now we said when the two highest priority group are on opposite side, that means they are against each other. You call it nth gen, which is the E configuration. Now E configuration means against each other because they are on different side. So that is the recap of E and Z configuration from our previous lectures. Now let us talk about the arrow and S configuration. Now before we talk about the arrow and S configuration, let's talk about the akira carbon center and then criteria for optical isomerism. Then we'll come back and talk about the arrow and S configuration. Now the question is, what is akira carbon center? Now akira carbon center is also called a stereogenic. Now this is an old name. A stereogenic or asymmetrical is also called a stereogenic or asymmetrical carbon center. Is also called a stereogenic or asymmetrical carbon center, and it is a carbon center. It is a carbon center with four different groups, about it. So that carbon center with four different groups about it is called a akira carbon center or a symmetrical carbon center. Now what does this mean in reality? For instance, if you look at, let's say this compound, let's say you have C, then this is hydrogen, this is CH3, now this is OH, and then this is, let's say, B arrow, and then you have another compound that has C, hydrogen, B arrow, and then OH. Now if you look at this carbon center, carbon is tetravalent, right? Yes, that is agreed. Carbon is tetravalent. But when you look at this carbon atom, you agree with me that the groups around it are 4 different groups. Look at this. You have hydrogen here. It's different from bromine, and it's different from OH, and it's different from what? CH3. There are no 2 groups here that are the same. So we can say that this carbon center is a chiral carbon center. Okay? It's a chiral carbon center. Now, how about this? If you look at this, you have this hydrogen and these hydrogens are the same. So this carbon center is not a chiral carbon center. This is not a chiral carbon. So a chiral carbon center, which is also called the asymmetrical carbon center, is a carbon center with 4 different groups about it. Now, in some compounds, like when you talk about the structure of glucose, it could have more than 1 chiral carbon center. It doesn't mean that the compound must have just 1 chiral carbon center. For instance, let me take an example like a glyceraldehyde. The structure of glyceraldehyde is glyceraldehyde is a carbohydrate. The structure is C. Structure of glyceraldehyde is C. Then you have double bond O, H, C, O, H, and then CH2OH. Now, you agree with me here that this carbon center here is chiral. Now, why is it chiral? Because it has 4 different groups around it. You agree with me that this group is one group, this is another group, this is another group, and this is another group. So any of those carbon centers that have 4 groups around it is a chiral carbon center. Now, how about glucose? Glucose is C double bond O. When you get to 200 level in CHS, you get an understanding of this better. Then OH, hydrogen, C, here is OH, hydrogen, C, OH, hydrogen, C, OH, hydrogen, and then we have CH2OH. Now, if you look at this structure very well, what can we say? Now, you agree with me that this carbon center here is not chiral. Why? Because there are only 3 groups around it, which is 1, 2, 3. Now, if you want to even consider this one as 2 double bond, it means that these 2 are the same, and hence this carbon center here is not a chiral carbon center. Now, how about if you look at this carbon center? Now, when you are considering this one, this from here like this upward is one group, right? Now, that group is different from what you have here. Is that not so? It's different from what you have here, and then we may consider this whole group here as one group. So in total now, we will say we have 4 different groups, because what we have here is different from what you have here, different from what you have here, different from what you have here. So this carbon center here is a chiral carbon center, and mark it good. Then remove all these whatsoever we have here. Now, how about if you consider this carbon center here? Is it chiral? Now, what you do is circle all the groups about it at all sides. This side you have hydrogen, this side you have OH, then this side you have this group here like this. Okay? Now look at the groups. Are they different groups? This group is different from what you have here. It's different from what you have here. It's different from what you have here. So we can say that this carbon center here is also a chiral carbon. Now, if you do that for this, you agree with me that this is also chiral and this is also chiral. So we can say that for glucose, we have 4 chiral carbon. So the chiral carbons in compounds are not always restricted to be 1. They could be more than 1 depending on the kind of compound that is given to you. Now, the number of stereoisomers that can be formed from a chiral carbon is given by 2 raised to the power of n, where n is the number of carbon centers, or chiral carbon centers. So for glucose that have n is equals to 4, the number of stereoisomers would be equal to 2 raised to the power of 4, and 2 raised to the power of 4 is equal to 16. So in this case, so that is that for chiral carbon. Oh, we are talking about colligative properties here. Sorry about that. The board was made for colligative properties. Okay, sorry about this. This is not colligative properties. Okay, so that is that for that particular chiral carbon center. So in some cases they may give you compounds and they ask predict the chiral carbons. You should be able to predict that. Now, criteria for optical isomerism. Now, one of the criterion for optical isomerism is optical isomers, they must have a chiral carbon. They must have a chiral carbon. That is one of the conditions. Number two, they must not be a racemic mixture. They must not be a racemic mixture. Now, talking about optical isomerism, let me give a detailed explanation of optical isomerism. Now, optical isomerism is the ability of some compounds to rotate light, to rotate plane polarized. Plane polarized light means light that is traveling in one direction. To rotate plane polarized light either to the right or to the left. Now, when it rotates to the left, you call it levo rotatory. Now, if it rotates to the right, you call it dextro rotatory. Now, what I mean by racemic mixture is, now the levo rotatory is usually indicated by plus, and then levo rotatory by minus, and then dextro rotatory by plus. Are you getting in that plus? Now, what I mean by racemic mixture is the amount of the D form. That means it must not rotate the same amount, like 50% to levo rotatory and 50% to what? Dextro rotatory. If it rotates 50 to levo, 50 to dextro, it means that the light will still what? Go straight. Because this one is giving 50%, 50%, it means it's not rotated to any of the direction. That's what I mean by racemic mixture. So racemic mixture means the D and the L form, that means the dextro form and levo form must not be in the same amount. For instance, 50% and what? 50%. 50 plus 50 will give us a total of what? 100%. If it's in this form, then that compound is not optically active because it's not rotating the light to any of the directions. Is that understood? So those are the conditions for optical activity. Now let's come back to the arrow and S configuration. Now for the arrow and S configuration, what you usually do is it also follows the Ingold Prelog rule. The arrow and S also follows the Ingold Prelog rule, whereby priority is assigned to the groups around it. For instance, if you have C, then let's say this is hydrogen. This is hydrogen. Now let's say this is bromine. This is CH3. And this is let's say fluorine. For instance, you are given a compound like this. Now the first thing you need to first of all look out for is this compound a chiral carbon center, or is this carbon center chiral or not? Now you agree with me that this is a chiral carbon center. Now let us assign priority to the groups around it in such a way that the one with the highest atomic number have the highest priority. So in this case, which of them do you think we have the highest priority? The one with the highest priority would be bromine. So this is 1. You give it number 1. Now followed by what? Fluorine. Then before what? Carbon. Because this carbon means CH3, CHHH before carbon. And then you now have finally hydrogen. Now the least priority group, in this case hydrogen, you don't usually consider it. Now what you now do is remove the least priority group, you don't consider it, then draw an arrow from the first to the second to the third, and the direction that the arrow goes will tell you the configuration, either the arrow form or the S form. So this is from 1 to 2 and then to 3. So this one goes in the clockwise direction. If it goes in the clockwise direction, you call it rectus or the arrow configuration. However, if you have it as something like this C, you have B arrow, then let's say you have F here, and then you have CH3, and then finally you have hydrogen. Now look at this one. Of course, we know this will be number 1. Here is number 2. Here is number 3, and here is 4. Told you that the 4 does not really matter. Now, so if you want to draw the arrow from 1 to 2 to 3, it becomes 1, 2, 3. Now, what direction is this? Is it the clockwise or anti-clockwise? Now, this is anti-clockwise direction. Now, when it's the anti-clockwise direction, you call it sinister or S configuration. Call it sinister or the S configuration. So that is that for the arrow and S configuration. So whenever it is given to you, you should be able to determine if it is the arrow or the S configuration, depending on the direction. Now, I said if it moves in the clockwise direction, what would you call it? Clockwise, you call it rectus, which is arrow configuration. While anti-clockwise, you call it sinister or S configuration. So that is that for that particular one. Now, there's something that we are not talked about. I think there's something we are missing, something I'm supposed to talk about. Okay, now you have a question. The question says, which of the following is optically active? Which of these compounds do you think is optically active? Is it A? Is it B? Is it C? Or it is D? Now, if you look at all the compounds very well, first of all, this is not a chiral carbon, right? This carbon center, let me start with this one. This carbon center is not a chiral carbon, so this is not optically active, because a carbon center, a chiral carbon center must have 4 different groups around it. So this is not optically active. Now, any compound that can be divided into 2 the same parts is not optically active. Okay, any compound that can be divided into 2 the same part is not optically active. Now, if you look at this compound very well, you agree with me. Now you can divide this in such a way that what you have here is the same thing as what you have here. Are you getting it now? So this compound is not optically active. They call compounds like the mesoforms. Is that understood? So this one is not optically active. Now we are left between this and this. Now, if you look at this compound very well, what do you see? Especially this one. Now, if you consider this carbon, let's consider this carbon. What did I say we are going to do? I said take this side as one group. So here is another group. Here is another group. And then this part is another group. So the question is this a chiral carbon? Yes, because this group is different from what you have here. It's different from what you have here. It's different from what you have here. So this is a chiral carbon center. Is that understood? So this one is chiral. Now, how about this particular one? Is it also a chiral carbon? Look at this very well. Is this also a chiral? Now, yes, this is also a chiral carbon center, and they cannot be divided into 2 the same form. So we say that this compound is optically active. This one is optically active. Okay, so that is how to identify optically active compound. First of all, identify the chiral carbons and see if they can be divided into 2 equal halves. If they cannot be divided into 2 the same half, you say they are what? Optically active. Now, coming to this carbon, you agree with me that this is a carbon center, right? Let's say this is the carbon center where 4 places meet. It's called the carbon center. Now this hydrogen here and this bromine, they are different group, but when you consider this one, they are looking like the same group, because if you divide it, what you have here is almost the same thing with what you have here. Number of carbon here is 1 2, number of carbon here is 1 2. Are you getting it now? Then you have CH3 separating them. So you can see that these two groups here are like the same exact groups, even though they are cyclic form. So this compound is not kira carbon, or that carbon center is not kira, but this is a kira, and hence option A is the correct answer to this question. So whenever you see a question like this, you'll be able to identify which of them is kira and which of them is not kira. Okay, now let us look at the next compound, isomers, enantiomers. Now enantiomers are optical isomers. They are optical isomers that they are optical isomers that are non-superimposable, that are non-superimposable mirror images of each other, that are non-superimposable mirror images of each other. Now what do we mean by that statement? It means that there are mirror images of each other that you cannot place on top of each other and they will lap very well. That's what enantiomers are. Are you getting it now? Now for instance, if you have, let's take the arrow and S form. What did we do for the arrow and S form? Okay, B arrow CH3 F, then that. Now let's say you have B arrow CH3 F, then hydrogen. Then you have B arrow CH3 let's say F, and then hydrogen. Now what configuration is this? This is 1, here is 2, and here is 3. This is going in this direction. Now this direction is what you call it clockwise direction, which is arrow configuration. Now how about this one? This is 1, here is 2, and here is 3. So you go from 1 to 2 to 3, and then you call this the S configuration. Now having ascertained that, let me erase this so that you get a better picture of it. If you look at these two compounds very well, what did you notice? If you look at the two compounds very well, what do you notice? You notice that they are the same compound, but what is the difference? This is like a mirror image of this. This is like a mirror image of this. Like you see this hydrogen here, then if you want to look at mirror images, it's just like this one is showing this way, then this one is showing this way. That's what mirror images are. Are you getting it now? But they are the same compound. So enantiomers are optical isomers that are non-superimposable mirror images of each other. So this is the arrow configuration, and this is the what? S configuration. And then you say they are non-mirror images, they are non-superimposable mirror images of each other. Now enantiomers usually have the D and the L form, but being able to identify that should not be your problem now. Just know that enantiomers are optical isomers that are non-superimposable mirror images of each other. Is that understood? Yeah. Now let's look at these questions together. Now the question says enantiomers are an example of dash isomer. So try and see if you get it correctly. Enantiomers are dash isomers. Okay, so which of them is the correct answer? Enantiomers are optical isomers. I've said it just now, that enantiomers are optical isomers that are non-superimposable mirror images of each other. So the correct answer is option A, which is optical isomer. Now the next question says, the following compounds have carbonyl group except. You should try. The following compounds have carbonyl group except. Which of them do you think have carbonyl group? And which do you think does not have carbonyl group? Now, the following compound have carbonyl group except. If you look at the carboxylic acid, their general formula is C double bond O. There you have OH. Now look at the amine. I told you that the general formula is C double bond O NH2. Now the amines CNH2, and then the ketone is arrow C double bond O arrow. So it's obvious the one that have the carbonyl group and the one that does not have. Carbonyl group is carbon and oxygen. Are you getting it? This one has a carbonyl group, this one has a carbonyl group, this one has a carbonyl group, but this does not have a carbonyl group. Hence, the correct answer is option C. Now let's look at the next question. The next question says, which of the following is the correct order of electronegativity? You have 1 minute to answer it. Now, which of the following is the correct order of electronegativity? Now, you have carbon. Carbon is, all this group here, they are almost in the same group apart from chlorine. So, chlorine is group 7. Let's bring out the groups of each of the elements. Carbon is group 4. Oxygen is group 6. Fluorine is group 7. Chlorine is group 7. So the correct order is, now in the same group, you agree with me that it follows the order, in the same period. Carbon, oxygen and fluorine are in the same period in the periodic table, so it follows the order. Carbon, if you look at the periodic table, I think I have a picture of the periodic table here. You have carbon, right? Then after carbon, what do you have? You have oxygen, you have fluorine, and we are told that electronegativity does what? Increases across the period. So if it increases across the period, it means carbon is less than oxygen, which is less than what? Fluorine. Is that understood? Then it decreases down the group. So it means that fluorine is more electronegative than what? Chlorine. So the order will be from carbon to oxygen to chlorine, then back to what? Fluorine. Because across the period, fluorine is the highest. Are you getting it? And down the group also, fluorine is the highest. But chlorine is greater than that of oxygen and what? Carbon. So it follows that carbon is less than oxygen, less than chlorine, which is less than fluorine. So the correct order is supposed to be carbon, less than oxygen, less than chlorine, less than fluorine. and that makes option D the correct answer to this question. Now you have the next question. This question is not supposed to take our time, okay? The following are true of nucleophiles except A, they are electron deficient species. Are nucleophiles electron deficient? They are not electron deficient, they are electron rich. So this one is not true. They attack partially positive center in organic compound. That is true. So this is not the correct answer. They are electron surplus species. That is true. So it is not the correct answer because we are looking for the one that is not true. They can donate electrons to compound. Yes, because of course they are electron rich. So the answer that is not true among everything here is option A. That makes option A the correct formula. Okay. Which of the following is false about mesomeric effect? Now, mesomeric effect is that effect that occur when an attacking species goes to where a double bond is. Are you getting it now? For instance, if a nucleophile attacks this during a reaction in such a way that this one packs up to give us CO minus, and then you have something like this, this effect here is called mesomeric effect, and it's only applicable in unsaturated system. Okay, now the question says, which of the following is false about mesomeric effect? Which of the following is false? Now it said they occur in saturated system only. Now this is false, and automatically this becomes the correct answer because they occur in unsaturated system. Is that understood? Now they occur in aldehyde. This is what? This carbon, this aldehyde. It can occur here. Are we getting it? Continuous propagation can occur as long as there is conjugation. Now that is true. It occurs in unsaturated system. All these are true, but this is not true. And we are looking for the one that is not true to get the correct answer. So that makes option A the correct answer to that question. Is that understood? So please take note of this. Which of the following will be most soluble in benzene? Now, note something, that polar solvents dissolve polar compounds. While non-polar will be more soluble in non-polar solvent. Benzene is non-polar because benzene is a hydrocarbon consisting of only carbon and hydrogen. So it will be soluble in only the compound containing only carbon and hydrogen without addition of oxygen, nitrogen, or whatever, because all those ones are polar. Now, if you look at option A, let the time start counting. If you look at option A, what can we say? This is polar because it has oxygen. This polar, it has oxygen. This polar, it has nitrogen. But if you look at option C, you agree with me that it contains only carbon and hydrogen. So what will be most soluble in benzene will be option C. And that makes option C the correct answer to this question. So that's how to solve problems like this, okay? Correct answer to this question. Now, next question says, hydrogen bonding occurs in compounds like the alcohol, whereby hydrogen is attached to a more electronegative atom. For instance, propanol. What do you see here? Hydrogen is attached to what? Hydrogen. So hydrogen bonding will occur in alcohols. So that makes option A the correct answer. Hydrogen bonding occurs occurs predominantly in alcohol, in the amines, because in amines nitrogen is attached to what? Hydrogen. And hydrogen bonding is only when hydrogen is attached to nitrogen, oxygen, or fluorine, or sulfur in some cases. Is that understood? So when hydrogen is attached to any of these compounds, you say hydrogen bonding is said to have occurred. That means option A, which is propanol and alcohol with OH, the correct answer. Now, next question. The following are permanent effects except I've told you that all these effects are permanent, but enantiomeric is not a permanent effect. Okay, all these are permanent, but enantiomeric is not a permanent effect. Enantiomeric is not a permanent effect. Please take note. Now, which of the following is correct about sp3 hybridization? sp3 bond angles 109.5 degree. So we don't need to solve. For sp3, the bond angle is 109.5 degree, and that makes option C the correct answer. I've taught you this before, right? Now, which of the following is not a characteristic of homologous series? They have the same functional group. Is that true? They have the same physical properties. Is that true? They have the same molecular formula. They have the same chemical properties. Now, the homologous series, they have the same functional group. That is true. They have the same physical properties. That is true. Although the physical property changes, but all ethers have almost the same properties. They have all esters have a sweet smell, sweet odor. Because when you're talking about physical property, you're talking about taste, you're talking about smell, talking about density and the rest. Although these properties, they gradually change or varies as they go down the group. Now, they have the same molecular formula and they have the same chemical property. This is true. But this, they have the same molecular formula, is not true. All members of the same homologous series do not have the same molecular formula. They may have the same general formula, but not the same molecular formula. Is that understood? For instance, propane, molecular formula for propane is CH3, then you have 8. Molecular formula for butane is C4H10. But these two compounds are in the same homologous series. Is understood? So for the fact that they are the same homologous series and they have the same general formula does not mean they have the same molecular formula. Compounds that have the same molecular formula but differs in their structural arrangement are isomers, are not homologous series. So the correct answer here to this question is option C. That is the correct answer. Now let's look at the next. What is correct about bond breaking except homolytic fissure result in the formation of charged species? Is that true? That is not true. Homolytic fissure result in the formation of what? Free radicals. We said this before. Heterolytic fissure result in the formation of charged species. Yes, it results in the formation of cations and anions. Heterolytic and homolytic fissure are types of bond cleavage. Yes, that is true. We said homolytic and heterolytic are types of bond cleavage. So this is correct. This is correct. Homolytic fissure result in the formation of radical. This is correct. So the correct answer is homolytic fissure result in the formation of what? Charged species, because we are looking for the one that is incorrect. Okay, and that makes option A the correct answer to this question. See how easy it is to just be marking your answers. Now, the following are physical properties except. Physical properties are properties like the melting point, correct, solubility, boiling point, refractive index. We have density, refractive index. All those on your physical properties. But reactivity, how you react with different compounds, how you react with oxygen, how you react with sodium hydroxide, etc. They are what? Chemical properties. Okay, the reactivities are chemical. While physical properties are melting point, solubility, boiling point, density, refractive index, etc. So the correct answer to this question is, because you are looking for the one that is not a physical property, and that makes option D the correct answer. Okay. Now next question. In solvent-solvent extraction, the two liquid phases must it be distillable? No, distill means to heat something to a high temperature in order to collect another thing. Must they be compactable? No, they must not be compactable. Dissolvable? No, they must be detectable. Now let me show you what liquid extraction or solvent-solvent extraction is, and then you'll see what I mean by being detectable. Now look at these compounds you have here. You discover something. Let me use this. You discover something. Now, in solvent-solvent extraction, the principle is let's say this thing dissolves in, or let's say this thing is present in this. You can see the solute particles here. All these particles, they are present in this particular solvent, okay? And then you want to separate them out. Now, how do you do that? How do you separate them out? Now, one way to separate them out is add another solvent, which they added here in this case. Add another solvent that is immiscible with this solvent that was there before, but can actually take some of these particles from here. Are you getting it now? It's not missing with this one here, but when you turn that solvent or that liquid inside this one, some of the particles from here will actually leave that solution and then meet this solvent here. That means it can dissolve the solvent, I mean the solute particles, but does not mix with the solvent. You understand? It can dissolve the solute particle. That means all these ones here, that particular solvent you are adding can actually dissolve them, can mix with them, but it's not mixing with the liquid itself. Do you understand the concept? So that is what solvent extraction is all about. Like this one now, you see, when they placed the other liquid, it was also like this. Then they shook the bottle or whatever. This is called the separating funnel. Okay, this is what is called a separating funnel. What actually happens is, after placing this one, you shake it, shake the layers. Now you discover that these solid particles that were initially here now, they are now on top of this solvent. They are now with this solvent. So in that case now, you can now what? Separate them out. Is that understood? You can now separate them out. Such a way that you decant this, or whatever you want to do, separate this one out and separate this one out. So you successfully separated the solute from the what? Solvent, by dissolving another solvent inside of it. Is that understood? So that is what solvent extraction is all about. Solvent extraction. Now, which of the following exhibits conformational? So, sorry, let's go back to that solvent extraction. Now, you see that the two liquid phases must be detectable, so that when you are carrying out your separation, you'll be able to detect that, okay, you've reached this one, or this one is another phase, and this one is another phase. If they dissolve, what will happen? The phases will not show. Now, you cannot distill them. It's not about being distilled. It must be detectable. Is that understood? Now, the following can exhibit conformational isomerism, except conformational isomerism is present in alkanes, whether straight chain alkanes or cycloalkanes. All alkanes. So propane is an alkane, ethane is an alkane, cyclohexane is an alkane, but conformational isomerism does not occur in ethene. Hence, the correct answer to this question is ethene. Now, which of the following is true about? All the following are true about resonance, except now there are some questions that you'll be given them. Most times you may not even have an idea of the other options, but because you have an idea of maybe one or two of the options there, that you know that this cannot be, that will give you an idea of what should be the answer. For instance, this question says all are true about resonance except A. Saturated compounds can exhibit resonance. Is that true? That's not true. Resonance is only possible with unsaturated because it's the localization of pi bond, and pi bond can only be found in what? Unsaturated system. Is that understood? So resonance is the localization of pi bond, and it only occurs in unsaturated system, not in saturated system. Saturated system cannot exhibit resonance. Hence, this one is not true, and we are looking for the one that is not true to get the correct answer. So this is the correct answer. You may not even need to go further if you know what you are doing. Now, this will say it is associated with the delocalization of electrons. That is true. Acetate ion can exhibit resonance. Acetate ion, this is acetate ion here, it can exhibit resonance. This acetate ion, it can exhibit resonance because this one here can enter here to form what? A double bond. It confers extra stability in compass. Yes, confers extra stability in compass. So all these are true, but number one is untrue, and we are looking for the one that is what? Untrue. That makes number one the correct answer. Now, which of the following compounds are only Lewis acid? I said Lewis acid are electron acceptors. Now, before they can be electron acceptors, they have either a vacant orbital or they have a positive charge. Either they have a vacant orbital or a positive charge. So if you look at these ones, all these ones, they are not Lewis acid. These ones, they are not Lewis acid. Are you getting it? We are looking for the one that are only Lewis acid. Now NH3, of course, is not Lewis acid, so NH3 disqualifies this group here. Now how about tin 2 chloride and boron trifluoride? I know boron trifluoride is a Lewis acid. Aluminium chloride is a Lewis acid. How about tin chloride? Now let's check where tin is in the periodic table and see if it's actually a Lewis acid. I think tin is group 4. Tin is group 4, so it has 4 valence electron. Now, does that mean Lewis acid are electron acceptors? Tin chloride, with what we have now, if you draw the electronic configuration of tin chloride, it becomes something like this, which of course have a balanced orbital. So is it H2SO4? H2SO4 is not a Lewis acid, of course. ACl is not also a Lewis acid. So which of them are we going to go with now? This is not also a Lewis acid. This NH3 disqualify this from being a Lewis acid because this does not have a vacant orbital. This one have excess electron, so it's actually a Lewis base. Lewis acid are electron acceptors. So I believe let's go with this because this one is the only one that has at least an idea of what we are talking about. And that is the end of this episode. Please make sure that you subscribe, turn on the notification button, and please take these questions very, very seriously. Thank you for your time.